This is session 2 of CuR Mini, and we are going to discuss about the physical design and manufacture of MiniBot. Oops, actually I should put this slide in last, but I'll go back to this. So first of all, I'm going to talk about the design of MiniBot, like why do we design it, the MiniBot in this particular way. So first of all, for design, you have the planning phase, and you are going to think about some questions. First of all, what objectives does the robot have? In this case, as we have the rule book, it's to compete with another similar robot to pick up target blocks in a set amount of time. That's our target. And in order to achieve this target and win against the other robot, you need to have some functions for that robot. The functions the robot should have is to be able to navigate the arena. It has to be able to avoid the opponent robot. It has to be able to locate itself in the arena. That's for it to be able to find the scoring point after picking up a block. And it has to be able to recognize and pick up blocks. So after we think about some of those functions, there are more functions to consider, such as like it should be able to follow a line and stuff like that. But those are more minor functions. Those are some of the major functions I can think of. And with those functions in mind, we want to consider what components we want to use. So some of the factors you would need to consider as well is the accessibility of the component. Like, is it a really niche component that you can't really find like on a common website? Would it often be out of stock or something? And you need to consider the price. We don't want to build a 200-pound MiniBot just for such a simple competition, right? And with that in mind, let's look at some of the common components. And all of those are used in the MiniBot. I'll introduce them one by one. So I'll go on to the actuators first. So actuators are components where you input signals or power and it will do something. And servo is one of them. The servo we are using is actually a micro servo with the name SG90. So if you type this SG90, you can find a lot on the servo. Like you can get a data sheet. You can get like the price of it on different sites, like produced by different companies, etc. And what it does is that it takes in an input signal. It would be a PWM signal. We'll talk more about PWM signal in the later sessions. That's to do with like microcontrollers and digital signals and stuff like that. So basically, you can think of it as a signal. So by signal, I mean you input 0 to 5 volts onto one of its pins, and it will give an output that corresponds to a specified angle from 0 to 180 degrees. So for example, if you input, say, 2.5 volts, this motor will rotate until it has 90 degrees. So what this is useful is that whenever in robotics, you have a joint and you want the joint to have a certain angle, you use a servo there. And what we are going to use it in the MiniBot is that we combine it with a 3D printed parts to make a gripper. So let me just get one of the 3D printed gripper. So it kind of looks like that, and you can see that there is a slot in the middle that you put the servo along with a servo horn, and you plug it into the slot so that whenever the servo turns, it will move the gripper. And if you put two grippers together, as they are like binded together by those gears, they will you can use a single servo to control the gripper to close or open. So that's servo. And a DC geared motor. So I mean it's kind of trivial. It has like 2 pins that you just input like a voltage onto it. So it's the same as any other motor you've seen in A-level physics, say. The more voltage you put into it, like the more power output it has, it can move faster. And therefore it's different rotational speed depending on the voltage input. And usually for robots like this, you will need a motor driver, because it's not like you are there to move a potentiometer to change the voltage. You need you need a motor driver to control the voltage supplied to the DC gear motor. And that's basically what's moving our robot. Those are the two actuators we are using. And next, moving on to sensors. Ultrasonic sensor, HCSR04, one of the most common sensors in any of those microcontroller kits. So its output, it has an output that corresponds to distance to the surface of or obstacle the ultrasonic sensor is pointing at. So for example, you point it at the wall and it will return a distance. But note that it communicates with Arduino using digital signals. We'll go through it in detail as well in next session. But right now, why it is using digital signal, since it is returning a distance, which is kind of like an analog signal, is because the principle of it working is that it sends out an ultrasonic wave, and then it has a receiver, and by calculating the time between sending and receiving, it works out the distance for you. So next is the IR line following module. It has an output. It outputs a Boolean value. So if you've done coding before, Boolean basically means true or false, or 1 or 0. And it outputs 0 for reflective surface and 1 for a non-reflective surface, or when the surface is too far away. So you might think, why is this useful? Basically, when you have a white tape on the floor, and you put two line following sensor together, one on each side, when the robot tries to move off the track, one of the sensor would detect the tape because it's not in the middle of the two IR sensors anymore. And using that value, you can use it to correct how your robot moves. Therefore, it's called a line following module, KY033. And also, you might if you type in TCRT 5000, you might also get this. If you type this in Google, you might also get this. But actually, the IR module without the rest of the circuit, RT 5000, and that is actually this small bit here. It's a photo transistor. So it outputs actually an analog value, stuff with corresponding to light intensity, distance, stuff like that. But this module so KY033 corresponds to this whole module overall with all those chips integrated circuit, and it outputs only a Boolean value that makes it much easier to use. Yeah, this is just to clarify. And this is a oops, sorry, this is typo. It's supposed to be KY521. I'll change that later. This is an inertia measurement module, and what it does in common terms is basically a gyroscope. So it measures, when you put this on the robot, it measures the acceleration measurements in X, Y, and Z direction, and as well as 3 angular speed measurements, roll, pitch, and yaw. They basically correspond, if you're doing mechanics, you will come over this soon, or physics, I suppose, you will also come over this. Basically, yaw is angular speed in the Z direction, angular speed in the Y direction, so on. So yeah, so on. So basically, it returns 6 of those measurements. And what is it useful for? If you know the acceleration of your robot, for all time, you do some integration, you integrate acceleration twice to get basically distance, and therefore you can get the XYZ coordinates given the initial position and acceleration because at all times. And the angular velocity can be used you integrate it once to get the angle that the robot turns. So if you want to make a 90-degree turn angle, you will need to use calculations from the gyroscope or IMU. Yeah. And what is actually working is this chip in the middle, and all those just makes it much more easier to like this breakout board just makes a circuit so that you can use the pins here instead of those tiny little pins here, and so you can connect it to a breadboard and to Arduino. So yeah, that's basically how it works. This is the thing that actually does the work. Another of the sensor is the light sensor module, TCS 34725, really long one. What it does is it outputs RGB values along with intensity detected, corresponding to the direction where this module is like pointing at. And we will use it to recognize the target object in the arena. And very similar to the inertial measurement unit, is also a chip mounted on a breakout board with some pins here that makes it easy to connect to Arduino or breadboard. So when we've covered most of these components that we are using, let's go back to the component kit. I took a picture of one of the kit that is kind of finished, but I might need to add a bit more of 3D printed parts. Like so, but this is almost like complete. So what's in it is Arduino, Arduino Uno, breadboard, servo, 2 DC geared motor with wheels, ultrasonic sensor, line follower sensor, IMU, color sensor, motor driver, a ball caster. That's because like we only have 2 wheels, and we don't want and you need 3 points to support a robot. So we use a ball caster so it's not dragging any part of the robot on the floor. And 2 laser cut chassis, a couple of 3D printed parts, nuts, screws, standoffs, and Type B, USB Type B wire, and a screwdriver. So basically everything you need to assemble the whole robot to make it work. Great. So the reason we go through those common sensors is because like we've said that during the design, you think of what functions you want the robot to do. And with those functions in mind, we want to choose components. So only after a bit of knowledge of what the components does, you can like make a wise choice. And also keep in mind that all the descriptions I gave about those components are higher level description. They are not exactly how they communicate with Arduino. So for example, for the ultrasonic distance sensor, it kind of returns an analog value, but when it communicates with the Arduino, it only actually uses digital signal. And I also explained the reason. It is because that it measures the time in between sending and receiving the ultrasonic wave instead of like any other like magical method that just returns a distance. Yeah. So next I'm going to talk about the design of the robot. So you already know what components, you kind of know what components you want to use, and you want to achieve some functions. And it's time to put all those components together in a single robot. So usually you either choose a top-down or bottom-up assembly method. Top-down is basically you have your assembly there, you draw a sketch, and you decide, and then you draw a sketch of where each component belongs to, and then you try to make the components so that they fit onto the part in the assembly. And bottom-up, on the other way, is that you design your parts individually, and then you try to figure out how to put them all together in the assembly. I chose bottom-up assembly when I was designing this year's mini board. And next, you choose your components according to the functions desired. And we basically went through the different components. And you want to roughly locate where the components belong. So either you drag them along in the space, or if it is a mini board like this, you got 2 chassis, you kind of put them on different layers. Next, you want to get the CAD models of components. So GrabCAD is a really useful website. You would not want to like design or CAD Arduino board yourself because it's just almost impossible. I mean, not impossible, but it takes up a lot of time. And if you want to get the dimensions correct, that's really kind of tough. Like I can't do that myself. And braces and supports. So you would want to make braces and supports to make sure all of your parts fit onto the onto your chassis, because like a lot of the electric components, they've got mount holes on them, but it's not enough like to just use the mount holes and kind of put them on the chassis, because like you want to place them facing different directions. I'm sure a bit of example make this clear. And for braces of support, you kind of need to look up data sheets for dimensions. And also you can use kind of a more cheaty method, which is to reference dimensions if the part exists. And I think, yeah, I think we are on time. So I'll demonstrate what I mean by doing braces and supports, and also like to show you guys a bit of basic Cadding if you're not familiar with it. I'll stop the presentation for now and bring up my SolidWorks. So say you want to, I haven't handed out the kits yet, but if you look at one of the chassis, it looks like that. And you will want to know how you actually like kind of CAD all those holes in the right direction. And I'm going to demonstrate that for Arduino only because it's kind of irregular. So first of all, let's get a Arduino model from GrabCAD. I've already got this up. So if you search for Arduino Uno, and you want to either get a step file or SolidWorks part file. So the reason I didn't get a SolidWorks part file is that my SolidWorks is the 2018 version, and this is like a future version and it's incompatible. So I got the step file. Cool. So let's open up the part. So it's a step file. Oh, kind of taking a bit long. I'm not sure if it's because of the Zoom. Or it might just be because it's quite a complicated part, as you will see. Oof. There we go. So really complicated. It's got all those. Oh, it's actually, yeah, it's actually simpler than I thought it would be. But nevertheless, it's still quite complicated. And our goal is to create mount holes for this 4 holes here, as this is those are the mount holes that we are gonna attach the Arduino to the chassis. So let's bring up a new part. Oh, that's taking longer than usual. I guess I'll just try to demonstrate how you do it. So I call this the cheaty way. Is you use if you already got a model of the part, you just like open it, and then you use the smart dimension, reference dimension, and use this to figure out the distance. Great. So when you got all those dimensions, you can just open a new part, and then it's all some basic features. You open a new part, you go to Sketch, and then you use a extruded cut feature to cut the 4 holes on the chassis. But I feel like this might not be the best way you should learn, because it's kind of dependent on the part that the user created. If he was not that, like, if he didn't make it that accurate, it might affect it when you manufacture it, because after all, you are the person using the chassis that you make. So you might want to actually go and check out the data sheet. It's very easy to find one for Arduino. So that is what you should do. You should go and check the data sheet. And there we go. Like, for example, for this dimension, it's 50.8. It's a bit unclear, not sure why. Yeah, it's a picture from an article. It's 50.8 here, and it's that one, I think, is 50.8 plus 1.3. You can just go and have a check. 50.8 here, 52.07. Yeah, almost 1.3 plus 50.8. There we go. So those are the 2 ways you would do to, like, create the mount holes on the chassis. Same goes for all the other components. There's something else I want to show, but depends on whether we can, like, create a new file successfully. Oh, there we go. So I think this is taking up a lot of memory, so I'm just going to close that for now. Let's say that we want to create a chassis like that from scratch. All right, I think I'll just go through the concept of it quickly, because it's kind of taking quite a long time to load. I guess it's because I'm using Zoom at the same time. So I'll just go through the concepts of designing the chassis and 3D parts for mounting. Whenever you are designing something that's symmetric, it will be really useful if you use the mirror feature in the CAD model, because say, for example, it's almost entirely symmetric, and if you are doing the dimensions like from left to right, say you if this is 200 millimeters, this is 10, and you make this 100 and this distance 190, like toe from the from to this side. It would be really hard when you try to adjust, like, say, the width. Like, say, for example, you think this is too narrow, you want to increase it to, say, 220, then you need to change the distance of the 190 to 210 as well. So basically, whenever designing something that's symmetric, try to always use a line of symmetry in the middle and mirror everything from left to right. It's also very helpful when you're doing assembling. That is because you can just use, like, the central plane for a lot of the mating. So that's a basically general tip or rule of thumbs when you are doing CADing. Same goes for symmetric supports, so on and so forth. And also, I really suffered from not doing one of the parts symmetrically, and I'll come over to that later. No, actually, we'll talk about that now. So you may unmute yourself right now. I asked a question last session that if anyone saw a flaw in the chassis design, does anyone actually spot the flaw? So I'm not sure if you guys already, like, downloaded the CAD, but the flaw is still there, but it will be gone today because I'm gonna change the design. Okay, so I'm glad it doesn't have to stay as a feature. It is a bug and it's fixed. And I'm gonna tell you what happened. So you might also learn from my mistakes. Let me try to bring that up. I really should have, I'm not sure how long it will take to open it. Fingers crossed. So basically what happened is that one of the sides of the chassis, like this distance, is not smart dimension. So it's a, it was a random distance. It was a random distance, but it kind of looked right. So I overlooked it. But when I printed, when I laser cut the actual chassis, it turned out that it didn't fit together, the top chassis and the bottom one. That's why I realized it was wrong. Okay, here we go. So this is still the same design from last week. Looks normal here. But if you try to do this normal, that way, zooming, you can see that because you are looking from the top view, so this side and this side should overlap perfectly, but there's a gap here. And if we go on to see what's wrong with the part, that's the part. If we have a look at the sketch, I'm not sure if you can tell immediately what's wrong, but basically there's a 40 here and there's none here. That means this side is not dimensioned. If you look at its dimension, it's 42.94. So it's not smart dimension, and I overlooked the problem. But if you just focused on dimensioning one of the side and use a line of symmetry, you won't have such problems. So basically, yeah. And as there was something else not ideal about the base chassis, so I fixed this problem as well. So don't worry, like those of you who have OCD won't be bothered by this, because I feel like this is a nightmare for someone, like a nightmare that this is not the right length. But it will work even with this bug. Cool. I think that's enough for demo. I'll go back to the slides. Yeah, basically, and when you're doing Cadding, always be aware of real life constraints and limits. For example, what material you're using, whether there will be manufacturing errors, and what the wirings will be. So you always need to, when you're doing the CAD, obviously you don't CAD all the wires, but you need to consider where the wires can pass through. For example, if one of the component is like on one side of the chassis, and if you do not leave any holes for the wires to go through, that is obviously not correct. And also, it's impossible to get everything right at the very first go. So if something goes wrong, that's only normal, and you just have to revise the design. Next, let's move on to prototype, to manufacture. So I'll be talking about rapid prototyping for this session. First of all, is laser cutting. How you laser cut is that you make your sketch in the SolidWorks or any other CAD software, could be Fusion 360, for example, and then you generate the DXF file, and then you import to the laser cutting machine. And because it requires induction session in the Dyson Center, so I feel like I do not need to go through too much detail about how to use the laser cutter. The technicians there will explain very clearly what you need to do, and safety, and also safety precautions you need to take, for example. And info page about using the laser cutting is here. It's given, the link is given here. And some properties of laser cutting are like features. It's suitable for 2D parts such as chassis. And the rule of thumbs while design is to make holes slightly smaller. because the laser beams have a finite width and they will make the hole slightly larger than when you design it. So yeah, that's basically just another like constraint you have to keep in mind when designing in CAD, because not everything fits perfectly the way you would expect them to fit in a CAD. And laser cutting is only accessible in Dyson Center. It's potentially dangerous, and I don't think anyone would be allowed one in their room. And individuals won't really afford one, I'd say. Next up, 3D printing. The way you do 3D printing is that you generate an STL file from the CAD software. And STL is basically, it converts the shape into like vector-like file format that can be sliced via a slicing software. I would recommend Ultimaker CuR if you are new to 3D printing. It's a very easy to use software, and it converts it to G-code, which is something that a 3D printer would recognize. It kind of tells the 3D printer how to move the nozzle. And finally, just leave the USB stick with the G-code on the machine and come back a few hours later, and there you go. Nice and simple. So why do you use 3D printing? It's suitable for all small 3D parts. The rule of thumbs while design is to make holes slightly larger. As normal 3D printer, they work by accumulating materials like displace like just placing materials layer by layer. So what if you make a hole, say 3 mil, like the material will very likely to bulge out and kind of eat up the space in the hole. So basically opposite to laser cut, you want to make the hole slightly larger to make it the right dimension in the end. And factors you need to consider, settings on the 3D printer are support and adhesion. So what support means is that obviously, if you know how a 3D printer works, it prints layer by layer. You can't just let it print in thin air. So whenever you are printing a part that part of it is in the air, you have to generate supports like under it, and it is recommended to, like when during design, not to have those parts dangling outwards, because they might also become the source of failure when printing, and you're wasting a lot of material for generating support. Adhesion, something to do with 3D printing bad. If you don't use adhesion, that depending on the different materials you are using, there might be all kind of like errors such as deforming due to like deforming because of heating, or it might not stick to the bed very well. So that is something to keep in mind. It will be very clear if you want to do 3D printing to just look at a few YouTube videos. Yeah, and support adhesion, also something to keep in mind when you're designing 3D printed parts. And 3D printer are accessible in both Dyson Center and from our society. We have 2 society printers. So if you are feeling ambitious and you want to design, if you want to make changes to your kit, say you're not happy with the chassis, you can design your own chassis in the Dyson Center. If you're not happy with the gripper we gave you, or some of the other parts that you use to fix components, you can design your own, and we can print them for you. And finally, at last, not finally, but the price. I thought I should tell you about the price of printing in Dyson. Laser cut is free for undergrads, but you need to purchase materials, and it's around £2 for 300 to 600 mil MDFs, which is the most common material we use. And it's a slightly more expensive for plywood, but I think they're all affordable. And for the 3D printing, if you want to print something that you design yourself, it's £1 per 30 grams on one of those like cheaper 3D printers, and it's £1 per 20 gram on those better printers. But if you want to print anything for a mini board project, we can, and if you're don't have access to the Dyson Center, we can do it for you for free, and we can use our society printers to print you stuff as well. So finally, a summary of the comparison of these two rapid prototyping methods. Laser cutting, it's fast and accurate, takes minutes to do so, it's foolproof. It's like it won't really make errors unless you are not operating it in the correct way. And like the technicians will probably yell at you if they spot you doing something not right. And 3D printer, on the other hand, is slow. It will take hours to print a small component, and it may fail repeatedly, especially if you design it not in a particularly optimal shape, or you got something wrong with the printer setting, it might just fail. The recommended object to do for laser cutting is planar object. So for example, chassis base plates. And an alternative to laser cutting is to use sheet metal, but metalwork is much harder to use. And 3D printer is very useful for complex shapes, such as connectors, gears, pulleys. And the alternative is using a lathe or milling. And CNC, I think that's just computer control lathe or something. I can't remember the full name. As for accessibility, laser cutters are not usually used in home. They are hazardous. They can produce hazardous gas, and they may cause fire. 3D printers, affordable. You can get a cheap one for like less than 200 quid, and it can be used in home. But both of them are cheap to, like both of the manufacturing are cheap and fast. So that's why we are using them for mini board. Cool. And finally, I think I'll just share some of the, I'll just give some examples of the constraints in manufacturing. So this is when I'm in Dyson Center and making the chassis. The design used to be the chassis, bottom chassis. The design used to be 200 times 200 mil, but because each of those sheets are 300 times 600 mil, so if you try to print 200 times 200, you can't really fit 3 of them. That's why I changed it to 190 times 200 just to make sure I don't waste too much material. Otherwise, there will be an L shape here wasted. And that is an example of real life constraint. Yeah, and that is a picture of the laser cutting after I finished, and that's the 3D printer in the Dyson Center. And another constraint is often like you can't always expect to get the material you want because the Dyson Center have to order it as well. So I used both plywood and MDF. Ideally, I would just choose to use MDF only because that is it's reliable. Like plywood kind of bends when it is humid, and that is really bad for the chassis. But as there was not enough MDF supply that day, so I used some plywood for the top chassis where you are not going to mount that many components on it, and it won't matter that much, and it's not taking the weight of most of the component. So I used MDF for the chassis and plywood for the top chassis basically. So you can I mean you will be able to tell the difference when you receive your kits. So those are just 2 examples of the constraints in manufacturing. And it's always good to keep those in mind when doing your design, like even from the start. Finally, one last bit about manufacturing is places to get your electronic components. Farnell, very good for screws, nuts, bolts, all those mechanical parts. eBay, like you can get a lot of cheap electronic components. Amazon, yes, not very professional, but still you can get some of the components, especially when you're urgent. And this Pololu, good for robotics and electronics. RS components, good for electronics. AliExpress, really cheap components, shipped from China. It will take a bit longer, but most of them are really cheap and good for like amateur robotics like us. And yeah, I think that's all for today's presentation. And some action points here are to join the Slack workspace if you haven't. And at least one team member should have a CAD software installed on the computer and go on to play with the CAD model so you kind of know what it's going to be like. Team leads should look out for emails to collect kits. Ideally, and I think it's very likely that we will hand out all your kits before the next session. And the next session will be on actually how to use Arduino and the kit. And team members, you should get to know each other because some of the teams, they were formed because like you just have an idea of the team like ahead. And some of the teams are like a mixed from different colleges, so you might not know everyone that well. So it would be good that if you try to reach out to know each other and to agree on time and place to work on the robot. Some of the teams, they're not in the same college, and it would be kind of ideal if you can work in the Dyson Center because it's open and it's a really good place to work on robot. And yeah, so, and also I also got people asking me questions on like approximately how much time to spend on the project. So my answer is that it's usually like 2 hours outside the session per week, but it's really up to you because like the purpose of this project is to get you guys to work on it like yourself, and we are there just to assist you when needed. So it's really up to you, and we hope that you can get it working by the end of this term. Yeah, so finally, any questions?